We can solve a conditional probability problem using formulas, contingency tables, or tree diagrams. On any given problem, one of these will be easiest and one will be hardest. But which one? Knowing which method is easiest is like your gender. It's something you're born with and can never ever change under any circumstances whatsoever, no matter what, no matter how many difficulties it will cause you. Or is it? The only way to know which method is easiest is to try different methods on the same problem. If you do this with enough problems, you'll develop a sense of which method is easiest to apply in a given situation. Remember, every problem is not a nail. By doing this, you'll not only be able to decide on the easiest approach to a given problem, you'll reinforce your understanding by solving the same problem different ways. And incidentally, it will also allow you to verify the correctness of your answer. For example, suppose 60% of the callers to a bank speak to a person, with the remaining 40% leaving their phone number. Of these 40%, 75% receive a return call the same day, while 25% receive a return call the next day. Of those who initially spoke to a person, 80% will become customers. Of those who received a return call the same day, 60% will become customers. And of those who received a return call on the next day, 40% will become customers. Calculate the probability that a caller spoke to a person, given that they became a customer. So note that a person could speak to a person, we'll call that A, or leave their phone number, a complement. They could receive a return call on the same day, we'll call that D, or the next day, N, and they could become a customer. And of those suggest we know that a certain event has occurred, so we're dealing with a conditional probability, and so we want to find the probability of A given C. Now, this is quite a mess of information, but note that we're actually given a bunch of conditional probabilities, and so a tree diagram might be easier to work with. So the first branch is whether or not a caller talked to a person. So we'll split our path, our tree at that point. Either somebody talked to a person or they didn't. And we know that 60%, 0.6, did actually talk to a person versus the rest who did not. And of the people who talked to a person, we know that 80% became customers. And remember, those are conditional probabilities, so our branch splits into customers and non-customers. Now, of those who didn't speak to a person, some of them received a call back on the same day, that's D, and that's 75%, and 25% received a return call the next day. And note that between the two of them, that actually includes everybody who didn't speak to a person. So of the people who received a call back on the same day, 60% became customers, and the rest did not, so we can fill out that branch. And of these people who received a callback on the next day, 40% became customers, and the rest did not, so we can fill out that branch as well. If we multiply the probabilities along each branch, we give the probabilities at the end. So we can see the probability that a person became a customer, which is anybody who ends up at one of these three destinations, that's 0.7. And the probability a person became a customer and talked to a person, that's only the people in this branch. And so our probability of A given C will be. We could also set up a contingency table. In other examples, we've made the conditioning events the row labels. In this case, we're given the probabilities based on whether a caller talked to a person, A, got a call back on the same day, D, or got a call back on the next day, N. So these should be our row labels. But I forgot to set it up this way. However, the only thing that actually matters is that the cells of our table correspond to events that are mutually exclusive and include all possibilities. And in this case, we have set up a table that satisfies these two, so we'll use the table as written. Since these are whole number percentages, it's useful to consider what happens if there's 100 times 100, 10,000 callers. So 60% of 10,000 or 6,000 speak to a person. At this point, we don't know if they're customers or not, so we should review this as the total number. This leaves 4,000 who leave a number. 75% of those 4,000, or 3,000, receive a return call on the same day. Again, we don't know if they're customers or not, so we'll record this in the total. And 25% of the 4,000, or 1,000, receive a return call on the next day. Of the 6,000 who spoke to a person, 80% become customers, so that's 80% of 6,000 or 4,800, and the remaining 1,200 do not. Of the 3,000 who received a return call on the same day, 60% became customers, and the rest did not. Of the 1,000 people who received a return call on the next day, 40% became customers, and so 400 became customers and the rest did not. And it's useful to extend the totals and verify that we've accounted for all 10,000 people. So we want the probability that a caller spoke to a person given that they became a customer. So of the 7,000 people who became customers, we see that 4,800 spoke to a person. So the probability a caller spoke to a person given that they became a customer is going to be, which matches our previous computation.